Hello, I'm going to present the work entitled The Modified Generalized Multidimensional KP Equation in Plasma Physics and Fluid Dynamics in 3+1 dimensions. We have studied the following section using the line symmetry theory. We have classified the line point symmetries. We have reduced to ODE the equation with exact solutions. In the following section, we studied the line symmetry groups with new solution, and finally, we have obtained some conservation laws. We begin with an introduction. The modified generalized multidimensional KP in 3+1 dimensions characterizes the dynamics of solutions and the nonlinear waves in plasma physics and fluid dynamics. Several authors have studied some special cases of KP equation. The first case is with n equal 1 and without the variable z. In the second case was proposed this modification of KP equation. And in the third case was and L. Tantawoy proposed this generalized KP equation. We consider a one-parameter Lie group of infinitesimal transformation acting on independent and dependent variables, where epsilon is the parameter group and the function tau, C1, C2, C3, and eta are the infinitesimal. The infinitesimal generator associated with the group of transformation can be written by V. The solution space of KP equation is invariant under the Lie group of transformation provided the invariance condition, where this is the fourth prolongation of the vector field and delta is the equation. The following sections is the classification of point symmetries. Then the invariance condition gives us a linear system of determining equation in the infinitesimal eta, C1, C2, C3, and tau. By simplifying the system of determining equation, we obtain the following equation, and then we solve them. Then we obtain the following point symmetry for each case. We have obtained 4 cases. In the first case, we have 8 generators, and in the following cases, we have obtained some of the previous generators and some new ones. Therefore, we calculate the commutator table. We note that the table is symmetric with diagonal 0, and it's a closed operation. These are necessary conditions of all commutator table. With this, we calculate the following table. The adjoint table of the Lie algebra. We use the adjoint table to obtain the optimal system of the Lie algebra generators, and then we will use this generator to reduce the equation under study to other equations. Then we go to the next section, symmetry reduction and exact solution. By using this generator, we obtain the invariants W1, W2, W3, and U, and this PDE. And again, by using the line symmetry method, we obtain this reduction equation with the independent variable S1 and S2. By using the generator V5, we obtain this group invariant and this PDE, and by using again the line symmetry method, we obtain this ODE with a solution. This is the solution with the following graphic for different values of the parameters. By using this generator, we obtain the PDE1 with the first invariant group and then the PDE2 with the second invariant group. These are the solutions for different values of the parameters. Finally, in reduction 4 and reduction 5, we obtain these 2 plus 1 PDEs by using the last generator of the optimal system. And now, in the next section, we will use some of the generator to calculate the Lie symmetry groups and new solution. Considering the infinite symmetry generators and solving an equation system of initial problem, we obtain this. The one-parameter Lie symmetry groups G1, G2, G3, and G4 are translations, time and space translations. G5 is an scaling group, and finally the other groups are time and space dependent saved. Now, using these symmetry groups, we can conclude that if U is a solution of modified generalized multidimensional KP equation, then by applying the previous Lie symmetry groups, we can obtain the corresponding new solutions of the equation. In the following section, we study local conservation load. A local conservation load for our equation is a divergent expression like this, where epsilon is the solution space of the equation. For this, we use a multiplier Q, a function of t, x, y, z, u, and derivative of u. Every non-trivial local conservation load is equivalent to one that can be expressed in the characteristic form. We need to calculate t, x, y, and z. Then we find all multipliers by solving the determining equation with the Euler-Lagrange operator. The previous determining equation yields a linear determining system for the multipliers. We solve this determining system and we obtain the identity multiplier with the following local conservation load. Finally, we can conclude we have obtained the Lie point symmetries admitted by this equation, and we have constructed an optimal system of subalgebras and use it to obtain symmetry reduction and exact solution. And we have determined the Lie symmetry groups with new solution, and finally we have classified a local conservation laws. And that's all. Thanks for your attention.